Welcome 1200. We are doing our radioactivity lab today, and this is the equipment that we'll be using. This lab is going to be somewhat like the last other two, more specifically the interference and diffraction lab, in that I'm not going to say much about this experiment. It's all outlined in your lab manual, and the equipment we are using is just very basic. It's explained in your lab manual, so there's no need for me to go over it. What I should say is that the equipment that we are going to be using is minimal. It's just three things, right? We have our track, which allows us to mount our detector and our sample on, and I could place our sample at different distances from the detector in a measurable way. So I have our counter, detector, sample, and rail. That's all we have. That's all we need. So read your lab manual, and you could fully understand how this equipment works. That's about it. Let's just get to it. So there are three parts to this lab. Traditionally, there were four, and one part has been eliminated, and what I'm thinking of doing is including that in this video as a supplement. Like, I'll put it at the end, and maybe it'll be like a bonus section for you to do if you want. Maybe like extra credit or something. The procedure is not outlined in the pamphlet that you have, but I'll just supply something to you in a data sheet if I go ahead and do that. And that particular part that I'm referring to, it's interesting because with that experiment, we can analyze the activity of a sample, or specifically its half-life. Now, the sample that I have here that we're going to use for our first two parts, it is cesium-137. Its half-life is about 30 years. So what does that mean for us? Over the course of our measurements, the activity is going to be pretty much constant, right? We're not going to be able to detect any decay, right? But in the part that was eliminated, we have a special sample, and I don't know what that half-life is. It is going to be seconds long, at most a minute, I think, from what I remember. I'll know once I do the data, but it has a very short half-life, so we could analyze the rate of decay by measuring the counts over a certain interval of time. So anyway, I may include that, I may not, but anyway, let's focus on the first three parts of the lab. So let's get started with part one. By the way, I have two counters here, and we are going to use this one. This one here is just set up for illustrative purposes, and that's because it makes a noise when it registers a count. So you can see, if I put this close to our sample, it's gonna there's gonna be a high activity, and as I move farther along, much less. So there is a portion in part two where you are going to analyze the count rate at different distances and determine or verify the relationship between intensity and distance. So what we'll do for that part is mount our detector at a certain position and then take readings as we vary the distance from source to detector. And let's see. For the first part, we don't care about intensity and distance. We just want to. What you're gonna do is make a histogram of the counts that we'll be recording, and we will put this at a fixed position and not vary it, and take multiple readings. What your lab manual has you do is record the number of counts in a 12-second interval. So we're going to do that and then do it again. Another measurement of how many counts occurred over the span of 12 seconds. And then do it again and again and again, up to 25 times. Well, exactly 25 times. You'll make a histogram of that data, and then when everything is complete, you will plot or draw a line on that histogram of the mean value of counts 12 over 12-second intervals at 5 minutes. Okay, so you know what? It may sound a little confusing, but you'll understand what I mean when you look at the procedure. The reason I'm mentioning this is because we are going to do things a little bit different. So I have your handout right here. And what page am I on? Well, page 6 of 15, under procedure for part 1. With the source at a distance giving about 200 counts in 12 seconds, take 25 12-second counts. We are going to take 25 10-second counts. So hopefully this doesn't confuse you too much. Well, why did I say that? This is basic stuff, right? That's not going to confuse you. We're not going to do 12-second counts. We're going to do 10-second counts. And the reason we're going to do 10-second counts is so that we could, 1, get more accurate measurements, and 2, to make things easier for me. And the reason being is that if we have to take 25 12-second counts, I need to use a stopwatch. So I need to start the counter, start the stopwatch, and then after 12 seconds, stop the stopwatch and stop the counter right at 12 seconds, right? Which I was practicing, and I don't know why I'm always off by like a tenth of a second. Okay, maybe sometimes I'm almost dead on, but anyway, here's a more accurate way to do it. Programmed in this counter here is a timer. So I could program it to take counts for a certain duration of time. Unfortunately, I can't do 12 seconds. It goes from like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then it jumps up to increments of 10 seconds. So after 10, the next highest one is 20 seconds, then 30 seconds, and 40 seconds. So I wish I could set it to 12, but I can't. Anyway, because of that, because I can only set this to 10 seconds, we are going to take 25 measurements. Each one will have a duration of 10 seconds. And I'm going to be able to knock that out real quick, and we'll get real good, excellent results, accurate results. Now, that begs the question, perhaps, why did they want us to do 12-second intervals in the first place? Well, procedures part 1. 1 is they want you to determine the mean of the 25 readings. 2 is the mean 12-second value of the 5-minute count. Aside from those 25 12-second interval measurements, or in our case 10-second, they want us to determine how many counts we get in a 5-minute interval. And when we get that number, what we do is, according to number 2, divide it by 25, and that gives us the mean 12-second value of the 5-minute count. So you see there in parentheses, total counts in 5 minutes divided by 25. How many seconds is in 5 minutes? 300. What is 300 divided by 25? It is 12 seconds. So that's how they came up with the 12-second interval. So that when you do this part, it is meaningful to plot that mean value on your histogram. And that's like a nice round number for a extended long interval of time. 5 minutes, it's a nice round number, right? 5 minutes. Record the number of counts in 5 minutes. Divided by 25 and you get 12, which is a nice round number of seconds. So that's where the 12 comes. So for number 2 to be meaningful for us, if we're doing this at 10-second intervals, what we need to do is not time our long interval over the span of 5 minutes, but instead do it for 250 seconds. So I will give you that measurement. What I'll do is after I do the 25 separate measurements, each one over 10-second time intervals, I'll record the number of hits that we get over the span of 250 seconds. And of course, if you divide 250 seconds by 25, what do you get? You get 10 seconds. So that data will be meaningful in regards to our histogram. We'll be able to, as number 2 says, the mean, in our case, 10-second value of the, not 5, but 250 second count. And you'll plot that line on your histogram. So if this seems a little bit confusing, actually that's good, because that just means that the purpose of these counts wasn't fully understood by you. So kind of read it, think about what they're asking you to do, why is it meaningful, and then you'll understand why we are adjusting our 5-minute length down to 250 seconds, because we're doing it in intervals of 10 seconds for the first part. Anyway, let's get started. And I will put you on pause, get this set up. I'm going to put this at a position so that we are going to get, as a lab manual suggests, approximately 200 counts per 12 seconds. Or I'll try and put it somewhere where I get 200 counts per 10 seconds. And again, that's just a rough estimate. It's just somewhere in that area. And I won't be using this one again. I'll be using that counter. Our detector for that counter is mounted over there on that bracket. And let me find that sweet spot and let's start taking measurements. Okay, hold on. Okay, folks, I'm going to say a few words about part 1 to help you out with the analysis. And well, what I did was I just made a histogram of this data, and you'll see in procedures for part 1 it says a 4-count interval is suggested for easy comparison with the computer simulations you will do later. Now, we don't do those computer simulations anymore. We haven't done them in some 10 years, and for sure you're not going to do them. So that 4-count interval is meaningless at this point. There's no reason to make it 4 counts. But when I made my histogram, I went ahead and did a 4-count interval. And I didn't like my histogram. I think personally that if you're going to keep the intervals that small to 4 counts, there should be more than 25 measurements to get a nice histogram that illustrates the randomness and characteristics of this random process. So what I did was I made that interval much larger. In fact, what I did was I just did what is depicted in your pamphlet on page 6. There is a sample histogram there of what yours should somewhat look like. So in that example that they gave there, their intervals, their count intervals consisted of 10 counts. In other words, if you're looking at this with me, it says, well, their first bar is 170 to 179 counts. Then the second bar is 180 to 189 counts, and so on and so forth. So those are your 10 count intervals instead of 10. So that's what I went ahead and did, and I got a better looking histogram. And then of course you want to draw vertical lines on that histogram, like one that designates the mean, the your standard deviations, and so on and so forth. It's all in the procedures there, and that's all I wanted to mention. So have fun with that, and I'll put you on pause and get to the rest of the experiment. Okay, students, let's get ready to knock out part one. By the way, I put a lot of thought into sticking to the lab manual's 12-second interval versus the 10 seconds so that there wouldn't be any confusion. But you'll understand after doing this part of the experiment why I decided to end up going with the 10 seconds. So let's get started. We have our detector and sample at a good position, and let's do a 10-second interval count. So there we go. No stopwatch is needed, and after 10 seconds it will stop, and there you go, 181. We got 181 counts in 10 seconds. So what I'm going to do is record this. Whoops. And what you should do is record it as well. I am not going to provide you a data sheet with the information that we are obtaining right now. You can do that on your own. So our first interval, we'll call it measurement 1. It is 181 counts. So let's go ahead and do that again. And remember, we have to do this 25 times. Now, of course, I could have just provided this to you tabulated in a data sheet, but hey, if I got to sit here and do this, why not you go ahead and do it along with me? So that's 168 for the second one. And reset. Let's do it again. Well, let's see. Maybe midway I'll give up and just say, forget it. I'll provide it to you. See how it goes. So this is the third measurement, and it is 184 counts. Do that again. $182. That was for the fifth count, 172. $161. $151. So that was the seventh measurement. $161. I guarantee you I would have been messing up if I was starting and stopping a stopwatch. I would have been off by a little bit. And then I would have ended up redoing the measurement so that I could get it as closely as I could to 12 seconds. So obviously this is going to be done much quicker over the 10-second interval. So this is the 11th measurement, 191. I feel like I should be talking. By the way, the majority of these videos were made with just the mic on my cell phone. So most of the videos, 161, that was for measurement 13, now for 14. So most of these videos, as it turns out, have a low volume, which is horrible, right? I almost wanted to do them all over again. Well, I lied. There's no way in hell I was going to do them all over again, because at this point, I had done so many. Okay, that was the 14th measurement, 177. I didn't catch on to the quality of the audio because when I edit this, I'm listening to the audio with the headset. It's just some typical AirPods, and it always sounds really good. It wasn't until I watched one on YouTube that I realized that these are recorded at a low volume. But anyway, I now have an external mic. You probably see it in the background there. So the audio is, I'm sure, much better. So that was measurement 16. Now we're going to do measurement 17. And I guess I mentioned that too because usually I film these videos in the middle of the night. Right now I'm doing it during the day. And because of this external mic, it's picking up the audio from every single car that drives past my street, and it is very annoying. So, apologize for that. 161, that was for measurement 18. $194. So this is measurement 20, and again, if I was using a stopwatch, we'd probably still be on like 7 or 8 because I would have been redoing them. 176. So here is measurement number 21. 154. 177. This here is measurement number 23. 163. 196. And again, your lab manual says to place this at a distance that gives you about 200 counts in 12-second intervals. So I was going to try and put this at a place that gave me 200 counts in 10-second intervals, and I kind of tried to do that. You could see that it looks like it isn't. To get that 200 count in 10 seconds, I probably should have moved this closer, but I mentioned that because that is not going to affect our results at all. That's just an approximation of where to put it, so don't worry about that. Our histogram should look very good. Now 170 goes to the 25th measurement. We are almost done. We need one more measurement. So we need a measurement for 250 seconds. So this is what I'm going to do. I am going to, let's see. Let's see if I could program this to 250 seconds. Crap. Of course I can't. Now it jumps to after 90, it jumps to increments of hundreds. So I'm going to turn the timer off, and I turn the timer off by putting it on 0. And I'm going to go back to count. There are my counts. Well, let me check something. By the way, I have it on 1000 volts. If you were curious, the lab manual does talk about that. Counts. So let's reset that. And I need to determine how many counts I get in the span of 250 seconds. So I have a stopwatch in my hand, 1, 2, and 3. So we are timing how many counts we get in an interval of time, which equals 250 seconds. So now basically we just need to sit and wait for that time to go by. Right now we're at like 27 seconds. This is probably like my 75th video that I've made, and I've always I'm always talking, so that I mean, this could be a lot to sit through, so that interest isn't easily lost in what I'm doing. I'm constantly like talking about the experiment, what I'm doing, and so forth. So it really seems awkward for me to just sit here in silence. I've never done this before, but anyway, we are at 70 seconds, and you guys, I suppose, can be bored along with me as we wait. That's 100 seconds. One 50 seconds. Think I'll get me a drink while I'm waiting. Apologize if that was loud. We are at 180 seconds, somewhere around there. All right, guys, we're almost there. We're about 15 seconds out. Okay, we are at 220. Okay, so I stopped the clock at 249.96 seconds, so that's pretty darn close. If I could have gotten all of them that accurate, I would have done the 12-second intervals, but like I said, I couldn't. I'd be bound to mess up at one point or another. But anyway, there you go. There is our counts 4,202. Those are the number of counts that we got in 250 seconds. So what you want to do is divide those counts by 25 to get the number of counts per 10-second interval. And there you go. I'll put you on pause and get us set up for the next part of the experiment. By the way, you guys have really probably did a great job with the last two labs. Those had a lot of analysis. What I'm trying to say is this one is, I think you'll find a lot easier. But anyway, let me put you on pause and get started with part 2. Okay, ladies and gentlemen, we are now ready for part 2. Now, for this part, we need to determine what the background radiation is, or noise. So I did this off camera so we wouldn't be too bored. And I determined that for you. What I did was I got rid of the sample, took it far away from our detector, and I let the counter run for exactly 300 seconds, or 5 minutes, and see what my count was. And there it is. You see it, 177. So I got 177 counts in the span of 5 minutes with no source present. So that right there is our background noise, 177. And let me write that down. Okay, now this is our mounting bracket for our detector, and the reference point is this needle on the mount, and it is at 0.00 centimeters. That will not change for the duration of part 2. It will always be at 0.00 centimeters. Now, our source, the reference point on our source, is right at the edge of the sample. Our sample is encased in this plastic box here. So right where the sample is located, the edge of the sample, that pertains to 7.90 centimeters. So let's see how many counts we get. First of all, let me get rid of our timer. Reset it. Now I need to time this. I do need the stopwatch for this part. And I will start 3, 2, 1, 0. Now, obviously the rate is extremely high, so I don't necessarily need, we don't need to time this for an extended period of time. Let's see, what should we make it? It almost doesn't matter at this point. I'm going to shut the timer off shortly. Okay, so here is our measurement. So the lab manual says to do 4 to 6 measurements. Each measurement is going to consist of our source being at a different distance away from the detector. So this is our measurement number 1, and we are getting 3,199 counts, and the time that it took to get these counts is 29 seconds, 29.91 seconds. Actually, we could probably just keep that to 3 significant figures, but there you go. Now, let me put you on pause and get us a different distance. So, be right back. Okay, so here's our new distance. The holder is mounted at, our sample holder is located at 17.00 centimeters, and we will begin counting. 3, 2, 1, 0. You can see that moving it only 10 centimeters away drastically decreases the rate. The question is, how long do we want to time this? Let's kind of play it by ear. Of course, what you'd want to take into consideration is your background noise. If you recall, we got 177 counts in the span of 5 minutes. Right now we have been timing for like 45 seconds and we're at 300. So we could probably safely say that we're just about there in the way of how much time we should leave this running. We're at 65 seconds. Maybe I'll make it an even 100 seconds. So we're going to stop shortly. Let's say another 20 seconds we'll stop. We'll call it quits right there. Ten more seconds. Okay, so this is what we have. The number of counts for position 2 is 653, and the time of those counts was 99.71 seconds. So let me put you on pause and get us a new position. Okay, hold on. Okay, ladies and gentlemen, we are now at our third position. Our source is at 27.00 centimeters, and we will start 3, 2, 1, 0. Now, our lab manual says to get like 4 to 7, I want to say, something like that, 4 to 7 different positions. I'm thinking of maybe doing more, but don't worry, you won't have to sit through it. If I do in fact get more, I'll take the measurements off camera, or at least put you on pause while it's collecting data, so that you don't have to just kind of sit here and count the seconds as they go by. Hey Alexa, who is Marie Curie?
According to Wikipedia, Marie Skłodowska-Curie, born Maria Salomea Skłodowska, was a Polish and naturalized French physicist and chemist who conducted pioneering research on radioactivity. As part of the Curie family legacy of 5 Nobel Prizes, she was the first woman to win a Nobel Prize, the first person and the only woman to win the Nobel Prize twice, and the only person to win the Nobel Prize in 2 scientific fields.
Hell of a woman. All right, there you go. Your little lesson today. We are at 86 seconds. Our first one was about 100 seconds. I think we should keep going. And of course, this is in consideration of our background noise. Remember, we're going to have to subtract the background noise from this. I mean, our background noise wasn't that much. It was 177 counts in the span of 5 minutes. So if you divided that by 5, that would be what? Somewhere around 30. Subtracting 30, or if we let this run for just 1 minute, I think we're good. We are going to stop shortly. And let's give it a few more seconds. Let's make it an even like 150 seconds. So we're almost there. Okay, so let's take this data. This is for our third position. We got 321 counts, And the time it took for that was 149.92 seconds. And I'm going to record the distance. That is 27.00 centimeters. Now let me put you on pause and get us a new distance for another data point. Okay, so I have a new position. Our source is at 40.00 centimeters, and we will start 3, 2, 1, 0. And I'm not sure how long I'll let this run, but you won't have to sit through it with me. What I'm going to do is put you on pause and get right back with you once I'm finished. Okay, hold on. Okay, we're back, and I am going to get ready to stop this. Okay, so this is for our fourth position. We have 377 counts. Now the time is 299.14 seconds. The position is 40.00 centimeters. Now, I stopped this at 300 seconds so I can illustrate this point. Remember, our background noise came in at 177 counts over the span of 5 minutes. So I timed this for 5 minutes, and you could see that our source isn't truly producing 377 counts. You need to subtract the background noise from this reading, which would give us 200 counts. So you can easily see that if I was to time this for a shorter period such that I registered 177 counts, we'd have to subtract the background noise, and it would just lead to inaccuracy. So we want to get a large enough amount of counts that are relatively speaking much larger than the background noise. So let me put you on pause and get set up for a new position, and it's going to have to run for a lot longer, I think, especially when we get to our last point, much longer than 5 minutes. But again, you won't have to sit through that. So hold on for a second. So our source is now located at 55.00 centimeters, and we will get started in 3, 2, 1, 0. So I'm thinking 8 minutes, something like that. And what I'll do is I'll get back to you once we, right before I stop the clock. So I'll put you on pause. Okay, so I am going to stop the counter shortly, and this would have been for 10 minutes. Okay, there we go. So the number of counts for this position is 561 counts. The total time it took was 599.98 seconds, and I'll record the position as 55.00 centimeters. So let me put you on pause again and get us another data point. Okay, we are now at the part of the lab where we do the dice experiment. It is called simulation of half-life decay using dice. 100 dice, we're going to toss them 8 times, and we have these containers here. They are labeled toss 1 through 8, and what you're going to do is solve for like lambda and the half-life, and then see how close those values actually are. So every die that rolled a 6 decayed. Now those tosses, they're labeled toss 1 through 8. Those are like increments of time. So each toss represents some time interval. Say 1 second or 1 year, whatever, doesn't matter. And well, these are a lot. Okay, let me just scan this real quick. I want to make sure that I didn't miss any sixes. Yeah, I missed one right here. And we are good. Okay, so that is our first toss. Second toss. Now pulling out the sixes, and again, this is gonna convince ourselves of that equation. So it'd be kind of pointless for me to just tabulate data for you, like if I did this off camera. Right, I could have just made up numbers to fit the anticipated curve we're gonna get. Okay, so that is all the sixes. This is toss 3, or 1 second. I'm sorry, or 3 seconds. Toss 3, or the 3rd second. Okay, see if this goes a little quicker now. Toss 4. I just accidentally tipped that one over. Let's see. Not very many, this one, on this run. That's it, really? All right. So this will be the 6th toss, or 6th time interval. All right. And our last toss. That is it. So, what we will do now is collect our data so that you can get the plotting. This is toss 1. Toss 1 is 2, 4, 6, 8, 10, 12, 14, 15. Toss 1 is 15. And toss 2 is 14. Toss 3 is 12. Toss 4 is 3. Toss 5 is 9. Toss 6 is 6. Toss 7 is 7. And toss 8 is 6. There you go. A truly, truly random process. I'll put you on pause and we'll get to the next part. Now the bonus part. So part 1 was the histogram where you were able to show the randomness of this process. Second part was proving the inverse square law. Third part was dealing with radioactive decay and half-life, but of course that was just a simulation. We used the dice. For this part, we're going to actually not do a simulation, but a measurement with a radioactive sample. Now, the sample that we were using before, we couldn't do this part of the lab with for obvious reasons. The half-life on that sample was some 30 years, so we'd be here quite some time. But we do have a sample that has, oh, and I mentioned this in the beginning, that had a half-life on the order of seconds. Okay, so I misspoke. It's on the order of minutes. And what we'll do is put the sample in the holder, butt it up against the counter, and take measurements. Let me go ahead and prepare that sample. Actually, I should probably put you on pause. Yeah, hold on a second. Okay, so our sample is in this container here. I am going to activate it by pouring some sodium chloride in here and putting it in this little vial. Put the vial in the holder and then measure its counts. And I won't tell you what this is. Just so that you can analyze this data on your own and determine the half-life based on our measurements here and not look it up online. So, if you bear with me for a second. Okay. I am activating it. This is called milking the generator. Come on, get in there. Okay, so there are our counts. In fact, I'm going to put it on the rate. So this is the rate. How many counts per second? Now it is going to decrease exponentially. And just by looking at the numbers, you wouldn't know that unless you're some kind of savant or something, right? Calculating this in your head. but it is decreasing exponentially, and this is how we are going to collect the data. I already collected the data. I'm just showing you the process on how I set this up. What I did was I used 2 timers. I put like an iPhone here and started the stopwatch so that it would keep a record of real time. And in my other hand, I used this as a stopwatch. So what I wanted to do was determine the number of counts in 12-second intervals over the course of, say, 3 or 4 minutes, or 5 or 6. I forget how many I did. But this is how I started it off. What I did was put the sample in and hit count. So it wasn't on rate, it was just counting like we did in part 1. So I hit count and hit the timer at the same time. And I timed 12 seconds. And right when it hit 12 seconds, so I shut off the stopwatch and I hit stop and record the number of counts that took place in that 12-second interval. I reset my timer and waited for 20 seconds to go by. This is real time, 20 seconds from the initial moment I started the iPhone clock. So when it hit 20 seconds, I started this again and hit count, and I waited for 12 seconds. I hit this at 12 seconds and hit stop on our counter and read the number of counts that occurred in that 12-second interval. Cleared my timer, cleared the counter, and looked at the real-time timer there until that got up to 40 seconds. When it got up to 40 seconds, I hit start on the timer, simultaneously hitting count on the counter, waited for 12 seconds, stopped this stopwatch and stopped the counter and read the number of counts that occurred in that 12-second interval. Recorded that, looked at the real-time clock until it got to 60 seconds. Then hit this stopwatch again, kept doing the process over and over again. So what I was left with was the number of counts that occurred in 12 seconds at 0 seconds, 20 seconds, 40 seconds, 60 seconds, a minute and 20 seconds, a minute and 40 seconds, 2 minutes, and so on. So this clock, those 0, 20, 40, 60, that was real time. That's never reset. And what we are going to do with that data is plot it. By the way, I forgot what this started off with. Was it something like 60? I think I want to say 61 per second when I first put it on rate. So look at the rate now. It's fluctuating a bit, but it has dramatically decreased, and it is decreasing at a slower rate. So the rate of decrease isn't linear. Again, it's exponential, as theory would tell us. Let me put it back on counts. So this is what you're going to do. You are going to, so I already did this for you, and I took the data as I explained, and I'm going to give you a data sheet. There are going to be 2 columns of data. One will be the rate, and the second will be the time, which represents real time. At what time did I have this rate? And that real time will be from 0 to, like I said, I don't know, somewhere around 3 or 4, maybe 5 minutes, whatever it is. I'm just trying to convince you right now that this is simple. This is an easy part of the lab. It'd be beneficial for you to do Why not? Especially if you get extra credit. So you'll have those two columns of data. And again, the first column will be the rate. It'll just be the number I read from this counter after a given 12-second interval. Now, what unit is that in? It is counts per, not unit time, counts per 12 seconds. The unit is counts per 12 seconds. So that will be on your y-axis. On your x-axis is nothing more than the time at which those counts were observed. It's either going to be 20 seconds or 40 seconds or 1 minute or 1 minute and 20 seconds and so on. And the units of that time is, of course, seconds. The reason I mentioned the units on the y-axis, counts per 12-second interval, is just so that, mathematically speaking, your units are labeled correctly. If you were to inadvertently label them counts per unit time, or for that matter, if you were to label those units as joules per kilogram squared, which is meaningless, right? But if you were that far off as to what the units really were, it still wouldn't affect your analysis. The curve that you are producing on that graph is going to give you the half-life. And the units of that half-life is independent of that y-axis unit. But anyway, counts per 12 seconds squared are your units. I'm sorry, counts per 12-second interval are your units. There are, what you want to do is determine the half-life of this sample. And the way that you're able to do that from your graph, well, you could do it a couple different ways. One way would be to pick a dot on that curve. Any dot. Let's say I pick one. That dot has a time and a rate. A time and number of counts. Okay. Let's say the counts are 500 and it occurred at some time t. What you want to do is go along that curve and find the rates or count that is half that original count that you picked, which was 500. So half that is what, 250? So go along the curve until you find 250 counts and see what time that pertains to. So that would pertain to a different t. Take the difference of those t's and voila, your half-life. So which points do you pick? Well, any ones you want. Of course, this is a random process, so every time you pick two different times, you're going to get a slightly different answer, but they should all be close to each other. An even more accurate way to determine the half-life is to do a curve fit. Now, from theory, we already know what kind of curve this is going to be, right? What kind of curve is that? Well, it certainly isn't linear. Well, it is exactly an exponential curve. So if you do a curve fit to this data, an exponential curve fit to this data, you will more accurately be able to determine the half-life. Just as you did in the previous section. You read up on, decay with the dice simulation and how to find the half-life, and same thing with this here. So what you would do is you do an exponential curve fit to your data, and you'll notice that on your curve fit it gives you this coefficient on the exponent, e to the something x. So that something, that coefficient on your exponent, can be used to determine your half-life. And it's just a basic calculation. I'm trying not to give too much of it away. it involves the ln of 2. Okay, I'll shut up at that. But that is an even more accurate way to determine the half-life. Well, maybe you want to determine the half-lives both ways. But anyway, there you go. That is how you would analyze this data. And let me check on the rate here. So it's around 3 counts per second. And remember, it started off as 61. So this is almost depleted, our radioactive source there. But anyway, I think I have said enough. Yeah, I guess I'll just leave it at that. Have fun with this analysis, and it has been a pleasure working with you this semester. And I don't think we'll see each other anymore. This is 1200, right? There's no 1300. So good luck with your endeavors, and maybe I'll see you around campus at some point in the future. Hopefully within a year, right? Anyway, have fun.